Welcome to Unit 5. This is, we're going to take a look at visual patterns. One of the major topics that we discuss in grade 10 is quadratic relations. And we want to be able to create formulas for them, and we want to be able to recognize them when we see them. So what this activity is all about is mostly to be able to recognize what is a quadratic relation versus what is a linear relation, as well as just some introductory steps to creating formulas for them. So basically the idea for this activity is to create the equations for the patterns that you see happening. Some of them are going to be linear and some of them are going to be nonlinear, and in fact they're going to be quadratic. So let's take a look at the first one. I'll leave the reading of the instructions to you. If you want to stop the video so you can read the instructions, then go ahead. But I'm just going to go ahead and start doing some of these. So we're looking at the number of leaves, and the number of leaves in this step is 5, and then in this step is 8, and then in this step is 11. And to get from 5 to 8, we're going up by 3. To get from 8 to 11, we're going up by 3. I'm going to assume that pattern's going to keep going. So the next one is going to be 14. And so because we're going up by 3s every time, this is definitely a linear pattern. And if you remember for your linear patterns, whatever that step is to get from one to the next, that is what your rate of change. So this is going to be a 3n. And then we're going to have to, so for figure 1, 3 times 1 is 3, but we need 5. So we're going to have to add 2 to that. And just double check that it works for the rest. 3 times 2 is 6, plus 2 is 8. 3 times 3 is 9, plus 2 is 11. So we're good to go. I will also leave you to figuring out what the number of leaves is in step 43, but you would do 3 times 43 and then add 2 to that answer. Wow, I guess that's 131, I guess. Okay, so let's take a look at the next one. We've got 1, 2, 3 in this step, and we've got 1, 2, 3, 4, 5, 6 in this step, and 3, 6, 9 in this step. And it looks again like we're going up by 3s, and so the number of stars equals 3n, and there's nothing else to add to that because 3 times 1 is 3, 3 times 2 is 6, 3 times 3 is 9. So we are fine with that. That's just going to be 3 times 43, which is 129. All right, I'm going to let you do the next. Am I going to let you do the next one? Let's see. 1, 2, 3, 4. That's got 5. That's 9. That's 11. That one is 3 by 1, 2, 3, 4, 5. That's 15. That's 17. Yeah, that one you can do. It's linear as well, so I'm going to leave that to you. Similarly, for the next one, it is also a linear relationship. And so is the next one. So I'll let you do those. I'm not going to do any more linear ones. All right, let's take a look at pattern number 6. So in step number 1, this is it says, what's the rule for the black squares and what's the rule for the white squares? So let's do the black squares first. So we have one black square here, and we have 1, 2, 3, 4 black squares here. We have 1, 2, 3, 4, 5, 6, 7, 8, 9 black squares here. Well, this is going up by 3 here, and this is going up by 5. That is not linear. And in fact, that is quadratic. So let's just put this in a table of values for a second. So when n is 1, 2, 3, 4, 5, 6, the number of black squares, I'll use B for black. We have 1, then we have 4, then we have 9, You might be able to tell me what the next one is. I hope you can. The black is a 1 by 1 square. This is a 2 by 2 square. This one is a 3 by 3 square. The next one's going to be 4 by 4, which is 16. The next one will be 5 by 5, which is 25. And the next one will be 6 by 6, which is 36. When you do the first differences, to get from 1 to 4, that's adding 3, then we add 5, then we add 7, then we add 9, then we add 11. That's not linear. However, if we do what's called the second differences, you'll see that they will show a linear pattern in the first differences. So that is a characteristic of a quadratic relation. Okay, quadratic. So the second differences have to be the same. They don't always have to be 2, they just have to always be the same. So this is a quadratic relation, and in a quadratic relation, you have a squaring feature to one of your terms. In a linear relation, you have linear terms. So terms that have no exponents, no nothing. The n is just an n. It could be multiplied by something, or divided by something. But the n, there's nothing else going on with the n. In a quadratic relationship, you always have a term that's being squared. There's always an n squared. And in fact, that is the formula for this particular relationship. So whatever your n value is, to get the number of black squares, you take that number and you square it. So then the number of black squares equals n squared. I'm actually going to leave the number of white squares for you to do because it turns out that it is linear. So I'll let you do that one. All right, let's take a look at the next pattern. Now, there are different strategies to solving for these patterns, and I want to show you 2 different strategies here. One strategy is to take what you have and arrange them in rectangles where the pattern of how the rectangle grows is consistent. So here, instead of making rectangles, what we actually end up getting is more squares. So this here, remember this for this one, n equals 1, n equals 2, and n equals 3. This is step 1, step 2, step 3. Here you end up with a 2 by 2 square. So when n is equal to 1, well, how do you get from 1 to 2? Well, you have to add 1. Well, let's just make sure that that's the same pattern. It looks like this is n plus 1 and this is n plus 1. Let's just make sure that's true in the next one. This is a 3 by 3. Yep, 3 is 2 plus 1. So this is also n plus 1 by n plus 1. And then 3, this is a 4 by 4. So yes, 4 is n plus 1 times n plus 1. So the number of diamonds that you end up getting is you take whatever n is, add 1, and then square that. You get n plus 1 times, which is the same thing as saying n plus 1 times n plus 1. Now, there's another way of looking at this pattern. I'm going to erase what I just wrote, and I'm going to look at it a different way. Sometimes when you're trying to figure out what the equation is for the pattern, what you do, whoops, I'll write that down again, n equals 1, n equals 2, n equals 3. So one strategy is look for squares. Try to make squares. Whether they are an n by n squared or an n plus 1 by an n plus 1 square, you're still just looking for squares. I'm going to do this one a little bit different. I'm going to look for n by n squares. So here is a 1 by 1 square. Here is a 2 by 2 square. Here is a 3 by 3 squared. So this is a 1 by 1 squared, which is an n square. that's an n square, that's an n square, because in this step, in the second step, n is equal to 2, so it's a 2 by 2 square. And in the third step, n is equal to 3, so it's a 3 by 3 square. Okay, so now what's left over though? Well, left over I have 3. And left over here I have 5. And left over here I have 7. Well, 3, 5, 7, that's a linear pattern where to get from one to the next, you're adding 2. So that's a 2n plus 1 pattern. So this all ends up to be n squared plus 2n plus 1. So n squared, that's 1 by 1 squared, plus 2 times 1 is 2. So there's 1, 2, plus another 1. Or n squared plus 2n plus 1. So n squared is the 2 by 2. 2n is 2 times 2, so 2 groups of 2, and then 1 more added on. And on the third one, you've got your n squared plus 2n, or 2 groups of 3, and then plus 1 more on top of that. So what this means then is, I'm going to erase this. What this means is that n plus 1 squared must somehow be equal to n squared plus 2n plus 1. Well, how does that work? Well, we already wrote down that n plus 1 squared means n plus 1 times n plus 1. And that just makes sense because to square something means to multiply it by itself. So what we have is a binomial. Here's a binomial times another binomial. So binomial, if you remember, is 2 terms. So what has to happen is when you're multiplying polynomials times other polynomials, every term in the first polynomial has to be multiplied by every term in the second polynomial. So we have to take this first n and we multiply it by the first n here, that's n squared. And we take the first n and we multiply it by the 1, which is a 1n. Then we have to take the 1 and multiply it by the n, that's a 1n. And we have to take the 1 and multiply it by 1, which is 1. And when we gather our like terms together, that gives us n squared plus 2n plus 1, which is what we said it had to equal in the first place. So then to get the number of diamonds in step 43, you would have to do 43 squared plus 2 times 43 plus 1. Or you could just do 43 plus 1, which is 44, and square that and get your answer. Oh, and back here, I guess I didn't say it, that would be 43 squared. Okay, let's take a look at pattern number 8. So for pattern 8, we have a 1 by 3 rectangle. Now remember, n is equal to 1 here, n is equal to 2 here, and n is equal to 3 here. This is a 2 by 5 rectangle. This is a 3 by 7 rectangle. So this is obviously n. So it's an n by, well, the 3, 5, and 7, those numbers, that is a linear pattern. And the linear pattern, because it's going up by 2's, the linear pattern is 2n plus 1. 2 times 1 is 2, plus 1 is 3. 2 times 2 is 2, plus 1, sorry, 2 times 2 is 4, plus 1 is 5. 2 times 3 is 6, plus 1 is 7. So the rule then is n times 2n plus 1. And when you expand that out, that equals 2n squared plus n. Well, why would it equal that? we should be able to come up with that pattern as well. So I'm going to erase this. If you need to see it again, rewind the video and watch it again. Okay, so we want to show that it equals 2 times n squared plus n. Well, that means I have 2 squares that are n by n. Well, there's a 1 by 1. There's another 1 by 1 plus n, which is 1. Here is a 2 by 2 plus another 2 by 2 plus 2 more. That's your n. Here is a 3 by 3 plus another 3 by 3 plus 3 more, or n. So this is an n squared plus an n squared, which is your 2n squared plus another n. This is an n squared plus an n squared plus another 2, which is another n. Here is an n squared plus an n squared plus another 1, which is another n. So it's 2n squared plus n. So you can use either one of those two. So those two things obviously equal each other. So you can use either one of those two to do the number of helmets at step 43, and I'll let you do that. Okay, pattern number 9. I think I'm going to let you do that one. You see what's going on and try and figure it out. Again, well, actually no. You know what? I'll do it with you. So I want you to try it. Stop the video. Try it. See how you do. And then come on back and see what you get. So when I'm doing this one, I see a 1 by 3. And then I see that both of them are adding 2 at the end. So there's a plus 2 on the end of both of them. Plus 2 and a plus 2. Here is a 2 by 4. Here is a 3 by 5. So this is an n, this is n, and this is n, because remember, n is 1, 2, and then 3. And then the number of column, or the how many squares there are in each row. There's 3, and then there's 4, and then there's 5. That is a pattern that's going up by 1 each time, so that's a 1n and then plus 2. So we've got an n by n plus 2 rectangle, so an n by n plus 2 rectangle plus 2 more. So we've got an n by n plus 2 plus 2 more. And if we expand that out, I'll do it over here, n times n plus 2 plus 2, which is n squared. So that n has to be multiplied through that bracket, so that's an n squared plus a 2n plus 2. Okay, well then that means that we could have looked at it this way. So let's take a look at what that looks like. All right, so here is 1 square. Here is 2 squared. Here is 3 squared. So there's my n squared. And then I'm left with 4, or I'm left with 6, or I'm left with 8. And 4, 6, and 8 is a linear pattern going up by 2 each time. So that is plus 2n plus 2. Because when n is equal to 2, when n is equal to 1, 2 times 1 is 2, but I need to get to 4, so that's 2. So it's made up of a quadratic part and then a linear part. So n squared plus 2n plus 2. And then for the number of blocks at step 43, you're going to do 43 squared plus 2 times 43 plus 2, whatever that happens to equal. Okay, I'm going to leave pattern 10 to you to figure out, but I am going to look at pattern 11. Pattern 11 is a lot more difficult because I can't seem to make rectangles with a similar pattern as it grows. So for instance, right now, this is a 1 by 2, which would imply the next one might be a 2 by 3, which is okay because I can put this square right here. And so I've got a 2 by 3, but I have nothing left over. And here I have 1 left over, and here I have nothing left over. And then when I make this one here, I say I put this square here. I don't have enough to make a whole other rectangle that's a 3 by something. So that's not gonna work. Or I could try to just look for squares. So let's try that. So here I have a 1 by 1, and here I have a 2 by 2, and here I don't have a 3 by 3 unless I move that one there. So now I have a 3 by 3. Here I've got plus 1 more. Here I've got plus 2 more. And if this is going to be a linear pattern, then I would need plus 3 more, but I don't. I've only got this one left over. So that pattern is not working. So there's another strategy that you can do here. What we can do is we can double the pattern and then half it later on. So double it, find the pattern, and then half it. So there's 3 here, so I'm going to add it upside down on top of itself. So now there's 6. And there's 6 here, and so I'm going to add it upside down on top of itself, and now there's 12. And there's 10 here, and I'm going to add it on top of itself upside down, and now we have 20. Okay, so now let's see what we've got. This is when n is equal to 1, 2, and 3. This is a 3 by 2. So that's an n plus 2 times an n plus 1. This is a 4 by 3, which is an n plus 2 times an n plus 1. This is a 5 by 4, which is an n plus 2 times an n plus 1. So it looks like the pattern is n plus 2 times n plus 1. But remember, that was double the number. So now we have to take that and divide it by 2. So the number of squares looks like this. So let's expand that out and simplify a little bit. So remember, every term in the first polynomial, which is a binomial in this case, has to be multiplied by every term in the second binomial. So n times n, that is n squared. N times 1 is a 1n. 2 times n is a 2n. So that's 2 times n is a 2n. And then 2 times 1 is 2. That needs to be divided by 2. That gives us n squared plus 3n plus 2. Each of those gets divided by 2, gives us an n squared over 2 plus a 3n over 2 plus 2 over 2, which is equal to 1. And so for the number of blocks in step 43, you're going to do 43 squared over 2 plus 3 times 43 over 2 plus 1, whatever that happens to equal. So that is sometimes a strategy. If you can't force rectangles or you can't count n squareds or 2n squareds or something, then sometimes you have to double your pattern and then half it. Or you might have to triple your pattern and then divide it by 3. Anyway, those are some strategies for figuring these out. I'm going to leave you to complete the ones that I skipped as well as do the rest of these on the sheet. And the solutions will be available to you. Good luck.